So I want to think about the isothermal expansion work of an ideal gas in a little bit more detail. Okay. Maybe. Okay, so let's talk about the isothermal expansion case. Isothermal expansion work of an ideal gas. All right, so the scenario here, we'll kind of draw a little picture. We have our, instead of a piston, I have just some sort of block weighing down my piston here, my whatever this is. And I have this fixed in place. I have some pins in here. And there's some initial starting volume and pressure, P1, V1. I'm also at some initial temperature, T1. Okay, so this is sort of state one. And when I remove these sort of pins holding it in place, okay, and I go to state two, what ends up happening is this thing will move up until it comes to some sort of resting position. Okay, this is a compressed gas at state one. And then I'm going to go to state two. It'll come to some sort of final pressure, some sort of final volume. It'll come to some sort of final temp, but I told you it's isothermal, so T1 is equal to T2 and delta T is equal to 0. This was my definition of isothermal. And I'm also going to tell you that P2, what it ultimately settles on, is exactly balancing P external. I'll wait until the pressure inside matches the external pressure. So P2 equals P external. So if I look at my, let's plot a PV diagram for this situation. Volume on my x-axis, pressure on my y-axis. I have some sort of initial pressure, one that I know is higher because my question told me or whatever, my gas was compressed. I have P2 or P exterior, these are the same, is at some lower pressure. I have some initial volume. I know I'm expanding, so I have some final volume. And so I'm going from essentially this position here to this position here. And I'm just telling you right now that the path that my gas would take to travel between these two positions is it's a curve that looks kind of like this. Okay? And so this is my isotherm. It's T1 equals T2 at some constant temperature. So the absolute maximum amount of work that could be done here by the system is given by the total area under this curve. Okay? This whole area here, from under the isotherm down to the axis, represents max amount of work that could be done. This is given by the area under the curve. And so what we can do is we can go ahead and plug in, we said it's an ideal gas, so we can plug in ideal gas law. So the work in going from 1 to 2 is going to be given by negative, we'll take the integral from V1 to V2 over P dV. And then I'm going to use ideal gas law to put everything, to substitute for pressure and get everything in terms of volume. So use ideal gas law to substitute for pressure. PV equals nRT. P is equal to nRT over V. And everything, I know everything else is a constant. The number of moles of gas isn't changing. The gas constant isn't changing. I told you it's isothermal, so T isn't changing. So everybody else is a constant. So I can now rewrite work from 1 to 2 as equal to negative, for convention, from volume 1 to volume 2 of nRT over V dV. I can pull everything out in front because it's all a constant. nRT, so it's my integral from V1 to V2 of 1 over V dV. What is the integral of 1 over something? Perfect, natural log. If you don't remember that, that's fine. Learn it now. If you want the proof of that, this isn't math. This isn't Calc 1 or 2, so we're not doing that. You just need to be comfortable using it, but I can point you to resources if you are like worried about not being fresh on that. Okay, so this is going to be equal to nRT, the natural log of V from V1 to V2, or negative nRT, natural log of V2, minus the natural log of V1. Yes, yay. And we can rearrange this, okay? The natural log of V2 minus the natural log of V1 is also equivalent. And again, if you're not familiar with this way that you can manipulate natural logs, I just need you to be able to use it, or I can point you to the proof that it works. Negative nRT, the natural log of V2 over V1. Okay? This is the equation as you'll see it. And this is work sort of maximum. The other way we're going to say this is reversible work. Okay? So what that means, I'm going to slide the paper back up for a second. Or actually, I'll just redraw it. Okay? So this was our diagram here. It looks something like this as we were going this direction. And we said maximum work was this area under the curve. Okay? In order to accomplish this, you would actually have to go infinitely slow, right? You would have to stay as close to possible as equilibrium at every. You'd move some infinitesimal amount and you'd wait for equilibrium to be achieved. And you'd move some infinitesimal amount and wait for equilibrium to be achieved. This is not real. It's not even possible to have this happen, right? So to have this sort of maximum amount of work, to accomplish this, to accomplish max work, we have to stay very near to equilibrium. At all times. And so this is infinitely slow. And also impossible. Okay, so what ends up actually happening is when I go ahead and release these pins, there's a really fast initial drop-off in pressure. And then I go over here, right? I get sort of a really immediate change to the external pressure, and what I only end up capturing is this part here. Okay? So all of the purple represents our max work, our also reversible work, if we could perfectly get everything back. The reality is just the square red area here after this drop-off. This is irreversible work. And for our irreversible work, so you might see it written like this, you might see it written like this, reversible or irreversible. The area under that curve is just, this was P2, this was P exterior, negative P exterior times P2 minus P1. Okay? The same one we've just been doing for our isobaric case. So like I said, reversible work, if you see the word reversible, we're talking about the maximum we could do. We're talking about some infinitesimally slow process that isn't real. Irreversible work is the real case. Where does this difference go? Where does all of this go in the irreversible case? The units of work are energy, so it's energy. And I can't destroy or create energy, so it must go somewhere else. What do you guys think? Sure. To the surroundings, perfect. In what form? Friction, sound, heat, exactly. It's losses to the environment in some form of vibration, sound, heat, whatever it is. The real life losses.